Okay. That was an adventure. Technology wins again here. So. I'm gonna do this. It's cool, folks. That help out? Awesome. Okay. Thank you. I think we should be all up and recorded and all of that type of stuff. So today what we're going to go through is just jump in, provide some pretty basic overview of general linear model. Okay, this is going to build on some of the stuff that we had gotten into in terms of last semester. That first semester starts about, we discussed primarily framing things within the context of means-based comparisons, which is good and appropriate for a lot of analyses. It's a nice way to go through and talk about things. However, limited in some ways, and so we're going to start to talk about how we can maybe start to expand how we think about analysis and frame it in just a slightly different way to give us a little bit more flexibility with stuff. Okay, so just a quick recap, right, on some of the primary analysis that we talked about in the fall. They talked about our independent sample t-test. Okay, with our independent sample t-test, here we're wanting to look at to see if we have evidence for differences across two populations. Okay, we've got two populations that we're interested in comparing. We've got population A, population B on some measure, right? And we don't know what the mean and standard deviation, mean or variability of these populations are, right? And we want to compare the populations, right? Katie, can we compare the populations directly?
No.
Why not?
Because they're just two separate.
They're two separate things, yeah. Sure. And why can I rarely, if ever, actually measure my population?
Because we'll never truly know. Can't get like everyone in the whole world.
Exactly, right? There's no way to capture everybody. I don't have the time or the resources or the capacity to capture everybody in the population. So do I just throw up my hands and say, well, I guess I'll never know? No. What do we do instead? What tools do we have at our disposal?
We gather samples instead when we compare the samples.
Yes. Gather samples. And Elizabeth, what are we hoping that sample, what characteristics are we hoping to see in the sample?
We're hoping that it'll be representative of the population. So you want like a larger sample size.
Exactly, right? So we want to go through, we've got a population of interest. Can't capture everybody, but what we can do is we can try and get a sample of people that we're saying is a proxy for this, right? It's going to be representative, right? Now, if I go through and I pull a sample from population A and a sample from population B, right? And I measure them on whatever I'm measuring them. Even if those population values are equivalent, are my samples going to be equivalent? No. Why not, Sam? Right, and so we've got some problems from a practical standpoint of actually grabbing a truly random sample, so we're probably going to have some bias. Yeah, what else? Sampling error, absolutely. I'll give you a what is sampling error? Tell me what sampling error is.
It's like when you take samples, you're never going to be able to choose.
That's true, but is that sampling error? Yes, Sam. Yeah, exactly. Even if I had the best sample, I've got a fantastic sample that is truly, truly random and representative, right? Do I expect that sample to match the population parameter exactly? No, it's always going to be off by a little bit, right? And that's what we're calling our sampling error. It's always going to be there. We can minimize it. We're never going to get rid of it, right? And so the question is so I've got a sample from sample from population A, sample from population B. Those two samples are never going to have the exact same characteristics, even if the populations are equivalent, right? So we need some test, some procedure to try and say, boy, to what extent do I have evidence that the values drawn in both of these samples are coming from populations that have truly different values? And this is where my independent sample t-test comes in, right? What I'm trying to do is get a big enough sample, right, from each one of these populations to say, sample statistics or my sample means are always going to be different to some extent. Does the difference that I see exceed what I would expect just based on sort of random sampling error, right? And if we've got a lot bigger discrepancy between these two samples than what we would expect based on just random sampling error, then we're going to say, you know, we've probably got evidence for a likely difference across the populations. If we don't, then we're going to say, well, these samples are different, but we don't really have too much evidence for, or strong evidence that these two populations do really differ in terms of their parameter of interest. Okay. Now, Bosch, if I do find that, if I find that I don't reject the null hypothesis, or I fail to reject the null hypothesis, and I say, boy, I don't have enough data to say that these populations, these samples are drawn from populations with different values, can I say that there's no effect? Why not? Okay, yeah, the effect size is semi-independent from sample stuff, right? But in terms of my interpretation, if I get a null result, can I say that there's no difference in these there's no difference in these populations? There's always going to be some difference, but maybe not, right? Maybe these are populations that are truly equivalent. But why can't I interpret a null result as evidence of no difference? Yeah.
Because we don't know.
Yeah, right. We're not saying that there's not a difference. We just can't say that there is, right? And remember, that's the crux of our null hypothesis testing. So I was just talking with Natalie about some power issues, right? If I'm going through and I test my hypothesis and it comes up null, can I say that there's no effect? Probably not. I can say I don't have evidence for an effect, but it's kind of ambiguous, right? It's inconclusive. That's a good word to sort of have in your repertoire. Results are inconclusive. I can't say if there is. I don't have evidence to say there is. That doesn't say that there's not. Now, if I have really, really massive samples, if I'm comparing a sample of 10,000 here and 10,000 here, and I really find that my p-value doesn't break 0.5, I can probably say it's a pretty strong evidence that they're pretty similar, right? And this is where some of our confidence bound starts to come. We can say, if I've got a confidence bound that really tightly falls around a zero difference, I can say, well, so this is looking like a near null value. But at the end of the day, for most of our routine procedures, we're just saying, we either say, yeah, we have some evidence, and it's not a yes/no thing, right? The strength of our evidence changes dramatically depending on sort of characteristics of our design and our results and things like that. But if we do find a sort of conclude a null or fail to reject a null, what we're doing is we're just saying results are conclusive. Can't really say one way or the other. Kind of get people sort of back in the saddle in terms of stuff that we're talking about this semester. Second year students, is this sounding familiar? Any questions from you all? Okay. So, independent sample t-test, one of sort of it's the basis for the vast majority of our mean space comparisons. But we also have something called our paired sample t-test. Okay, remember our paired sample t-test, our null hypotheses here. We're generally using this in a repeat measure situation, right? Where I've got two assessments at two different time points with the same group of folks, and my null hypothesis here is that the population difference score is 0. If I measure Rachel today and I measure Rachel a week from now, and I have an infinite population of Rachels, my hypothesis is that the mean difference score from time 1 to time 2 in the population of Rachels is equal to 0. There's no difference, right? Rachel does not change in terms of those different scores. My alternative hypothesis is that the different scores in the population is some non-zero value, right? It's either going up or going down, just not 0. Okay. And again, here what we've got a hypothetical population of, if I were to take all college students and measure them at the beginning of the semester and end of the semester on something, in that hypothetical population, what's the difference in these scores across time, right? And what we're looking at this test, do we have enough evidence based on our sample to conclude that yes, the different score in the larger population is likely some value that's different. So this is our basic repeated measure design here. Questions? Then we finished up talking about our ANOVA, right? Basic structure here. What we've done is sometimes there's going to be situations where maybe I want to compare more than 2 groups. Maybe I got 3 groups or 4 groups, right? Well, we've got a plan for that. It's called our basic ANOVA, right? right? So we've got one population, two population, three population. Can't measure the population directly, so what we're gonna do is we're gonna draw samples from those populations. And the assumption is things are represented. And what we see are differences to some extent across these three sample means. Our test is designed to go through and say, do we have enough evidence? Do these populations differ to a great enough degree for us to conclude that yes, these samples are likely pulled from populations that differ on whatever parameter it is that we're interested in. Okay, and again, two possibilities. One, differences that we're seeing here in this slide here could be just the result of random fluctuation in sampling error. Like it's just going to change sort of by small degrees to some extent, right? Is it sampling error, or do we have actual differences in these populations that are producing different means, right? You see these downward arrow, because what we've got is the population is producing differences across these samples, right? It's not just happening by chance. We do have different values across these different populations that are driving the differences that we're seeing across these groups. And we're using our ANO to go through and say, do we have evidence for this? Okay. Now, when we're talking about our t-tests, we're generally talking about the difference between groups. What's our unit of evaluation for our ANOVA? What are we using? Yeah. Yep, it's an F statistic. Good. But conceptually, what are we looking at? Are we looking at differences? Kind of, but how do we get around the fact that I can't calculate the difference between three means? Yeah.
Like an omnibus test?
What's that?
Omnibus?
An omnibus test. What's that omnibus test looking at? Two of the populations, right? What's the unit? What's the measure we're using?
Variance.
Variance, right? Do I see variability in the data? If I have no variability across these scores, if I say there's no variability in mean score across the sample, what does that tell me about those sample means?
No difference in variance across them.
Yeah. So what does that mean about the means?
That they're approximately equal.
That they're all the same. If there's literally no. If I have no variability across the sample means, it means they're all the same, right? If I've got a lot of variability across my sample means, it means that there's lots of differences across here, right? So what we're doing is we're harnessing this principle of variability as a proxy for differences across a group of scores, right? Remember, second years that we're talking about a distribution that has no variability, it means everything's the same. We've got a distribution with a lot of variability, it means it's kind of all spread out, right? So if I'm looking at variability across these means, this is what we're doing with that test, right? We're looking at variability across our means, over the top of variability within our mean or within our groups, right? Because if my IV, if my factor is the only thing that produces differences in whatever I'm measuring, what should everybody's score in the same group be? Be all the same, right? If year in the program is the only thing that determines your performance on some evaluation, then that's it. Like your year of graduate school is the only thing that determines how you perform on something. Now, it's not a realistic situation. But if that were to happen, what would all the first years get on sort of this exam? Same score. What would all the second years get? The same score. Does that happen? No, because there's nothing that we ever look at that's singly determined by something, right? So we're always going to have some differences within our group, right? First years are always going to differ to some extent in the second years based on things that we're not actually measuring, right? And so we'll call that, what do we call that within variability? Context of our model. Error, yep. It could be systematic, it could be non-systematic, but if we're not measuring it, it's by definition error. There are differences that aren't accounted for, and so that's error in our model, right? And so with our annual, what we're looking at is the variability across our scores, or across our means, versus the variability on average that we're seeing within. And if we see the differences across our means is much greater than the variability that we're seeing within groups, then we've got a large F ratio. We're probably going to reject the no. If the differences that we're seeing across mean values is about the same variabilities we're seeing just within groups, then we're probably going to get something close to 1, and we're probably going to fail to reject. First years, it's been about a month since you've had sort of been exposed to this. The second year is a little bit longer. Questions about what we're talking about here, but on the same page.
Just to ask again, when you said F test, that's because it's in the notebook, right?
Yep.
Okay. It's coming back.
There you go.
Might take me a second.
All right, so up to this point, what we've done primarily is looked at what we talk about or what we describe as univariate statistics, okay? Univariate statistics is just looking at, or univariate bivariate, we're just looking at one IV and one DV, right? If we're looking at our t-test, we have one grouping factor and one outcome. We're looking at our one-way ANOVA, we have one grouping factor and one outcome, okay? But our problem here, that they can start to get inefficient if this is all we have in our tool belt, right? What if I want to know the relation or association between gender and college performance, okay? Let's say I measure gender identity, and so look at relation to course load, class attendance, hours studied, college GPA, major GPA. I can do a lot of tests with that, but that's a lot of analyses to keep sort of going over and over and over again, right? We're also limited in the types of questions that we can ask, okay? These are trauma-related questions because it's easier for me to come up with trauma-related questions. But with my univariate statistics, I can say, what's the relation between trauma severity and psychological distress? Like, so does the impact, is the severity of the trauma, is that associated with distress? Do what men and women differ in psychological distress, right? Is there an association between social support, severity, PTSD? These are all fine questions to ask, but they start to get pretty rudimentary and pretty boring. If we've been doing this long enough, this starts to become not interesting, right? And so our solution here is start to expand our models to look into some multivariate statistics. Okay. With our multivariate statistics, here we're looking at modeling techniques that are incorporating, if we're just thinking singly multivariate, generally what we're talking about is some model with multiple independent variables and one dependent variable. Okay. What we can do here with this is, again, look at multiple predictors and multiple outcomes. Okay. I can say, here are my IVs of interest, here are my DVs of interest, and I can start to go through and start to model things in more creative ways. Okay. Another benefit of our multivariate statistics, I can start to capitalize on associations between different sets of variables that can be helpful in terms of power. Okay. If I'm running a MANOVA, I know Allison runs some MANOVAs, and I'm interested in looking at a set of interrelated outcomes. If those are interrelated in the right way, I actually get more power with that test than I might somewhere else. Start to capitalize on characteristics of the types of things that we're often wanting to look at. We can also start to expand the range complexity of questions. We can start to ask more interesting and elegant research questions. Okay, so instead of asking just what's the relation between trauma exposure and distress, I can start to say what types of things what factors start to change the nature of that relation. Right? Is trauma severity and PTSD, Natalie, going to be the same always and forever for everybody in the universe? Probably not. There's probably a whole lot of individual difference factors. It's going to change the strength of that relationship, right? And if that's the question we're asking, what type of question are we asking there? What do you know?
It's not moderation.
Yeah, it is moderation, right? Do I have a factor that's changing the nature of that relationship, right? So the relationship between trauma severity, let's say depression, is strong for people with this characteristic, but it's weaker for people with this characteristic. I can't ask that with a univariate design, but I can do that pretty easily with a multivariate test. Okay. I can ask what factors are accounting for the relation between trauma exposure and prolonged distress. Okay, so I know that trauma exposure is associated with increased stress, but what if I'm interested in why that's occurring? What question am I asking next? That's a mediation, right? What's the thing that's causing X to be related to Y, right? Again, I've got an extra variable and I can't really test that with the univariate test. And so I need to switch into a multivariate test here. What are the unique contribution to variance factors? The occurrence of PSYC. What am I, so here I just don't want to see if X is related to Y. I want to see if X1, X2, X3, X4 is related to Y. And I'm interested in the relative contribution of each one of these things to the prediction of my outcome. What am I talking about here? Yeah, it's a regression, right? So I've got a bunch of predictors, but they're probably not all going to be independent of one another, right? So I'm wanting to look at the relative impact, right? So what I can start to do is ask more interesting questions that start to get, it's always going to be a horribly simplified model of reality, right? But I can start to do more things that allow me to ask more interesting questions as I start to build on these statistics. Okay? So, Brittany, you were talking about, or I see you made a note about like having a hard time trying to figure out like what do I choose? Like what analyses do I run given my question, right? Generalize the general linear model. This is a nice sort of general all-purpose catch-all model that is kind of the umbrella model for everything that we've done up to this point, okay? Think about your GLM as your sort of basic internal combustion engine, right? Your lawnmower and your Ferrari have some similarities. Doesn't look like it on the outside, right? But if we get down to it, it's all working on essentially the same type of technology. This is your general linear model. This is kind of the umbrella model for that kind of coordinates the types of analysis that we're looking at. And what we're going to start to do is we get into some regression-based stuff this semester. We're going to start thinking about things in GLM terms. And it's going to help us organize analyses. It's going to help us select models that are appropriate. And it's going to set the foundation for you to go through and start to master some increasingly complex analysis. So, Rachel, you and I were talking. It sounds like you all are doing some really cool stuff, looking at some spatial analysis that I don't even know up and down, like how you look. But I'm willing to bet a great deal of money that sort of basic sort of principles of regression and sort of general linear models is going to apply to those analyses. If you're strong in that, use your foundation to go through and build on some additional stuff, right? Erica was talking, Ben and I were talking about some stuff that you're doing and sort of trying to deal with missing data and so on those lines. And how do we go through and restructure this analysis to account for some of that stuff? Again, this generalized linear model. So that if you understand the basic principles of that, start to get familiar with it, the additional stuff that you get moving forward will start to make some sense. But oh, I understand that. Yep, I understand why that would work, so on and so forth. Okay. So the basic assumptions of our GLM. Okay, we got a linearity assumption, okay, which makes sense given it's the generalized linear model, right? What we're assuming with our linearity assumption is that pairs of variables in our model are assumed to hold linear relationships with one another, okay? Essentially what this is saying that if I take any two variables in my model, the relationship between those two models should be adequately represented by a straight line, okay? If I plot those two variables out in a scatter plot, a straight line should do a pretty good job, or reasonable job of accounting for the nature of that relation. If I go to and I violate that assumption, what's going to happen is it's either going to make my associations appear smaller than they should be, or I could fail to detect relationships, or it could start to get spurious effects that aren't actually really there. Okay, so this graph right here, Robert, does this constitute a linear relation if we're looking at a scatter plot of husband's age and wife's age? What's that? Yeah. Pretty clear linear relationship right there, right? Pretty easy to see. What about this? So we've got, I don't know, this is just Google graphs that I pulled off. I've got horsepower and drive ratio. Okay, Basha, you look like you know a lot about horsepower and drive ratio. We have a linear relationship right there. No? Elizabeth says yes. What do you think?
Oh, me or her?
I don't know. You guys duke it out. Which one's going to be right?
I think so. Granted, there's like, are gonna be scattered on either side, but you can kind of see that downward relation.
Yeah, right? It's not as tight as that. We never get data that looks like that. That's ridiculous, right? This, much more consistent with the types of things you see, right? So yeah, we've got a negative relation, like, is there a better line that you can draw through that other than a straight line sort of going down that's gonna minimize the deviations from sort of your estimate? No, right? A line is gonna be the most parsimonious sort of line you can go down through and draw from there. So yeah, we've got a linear relation here, it's just a negative relation, right? What about this, Josiah? Is that a linear relation?
I think there is.
Okay, so we got so this is association between plot out education and income. Yeah, could we fit a line to that? Sure, we could fit a line to that, right? Does this look like a linear relation though, technically?
It looks kind of curved and linear to me. Is that the word?
Yeah, it looks like a little bit of a curvilinear exponential, right? If I go through, I mean, I could draw a line kind of here. Does a decent job of capturing most of this stuff, but I've got some folks up here. It looks like if I have some sort of maybe exponential or quadratic curve, a curvilinear relationship is actually doing a better job of accounting for that than a straight line. Could I model it as a straight line? Sure. If I model this as a curvilinear function, that's going to add to the complexity of my model, right? And if that curvilinear function accounts for an additional like sort of 0.5% of variability, it's probably not worth modeling it. But something like that, I'm saying of something that looks like, now, this is just one sample. If I got another sample, it could look different. But at least if these data are good, and I trust these data, it looks like a curvilinear function might be better. The problem, if I don't go through and account for that, is that if I go through and I draw a line here, and that line says, yeah, that kind of accounts for these things are kind of related, right? But if I go through and I model this as a curvilinear function, go something like that, then my model says, oh yeah, these two things are very much related, just not in a linear fashion, right? And so the risk that we run in applying a linear model to this, if the relation isn't linear, it makes it look like these two things are less related than they are. And then I'm going to say, well, these things are kind of related, but it's maybe not a big deal. In fact, that actually is, it's just not a linear function. Okay. So in the extreme, if we were to do this, let's say got this, and here's X, and here's Y. I go through are X and Y related here? We think just that. Yeah. Really related, right? If I know something about X, do I know something about Y? Absolutely. Okay. But what happens if I try and fit a linear function? Linear function looks like that, right? That says, it tells me that X and Y are not related with one another, right? And so the problem is when thinking about linearity and why it's so important to go through and screen our data and take a look at some of this stuff is we could have very strong nonlinear relations, right? But if we're not looking for them, if we're not screening our data, we won't recognize it. And then if we try and apply a linear function to it, it's going to tell us that X and Y aren't related to one another, or that X and Y are related only weakly, when in fact it might not, right? So we've got kind of a couple of different things. Anytime you have nonlinear component to a model, it increases the complexity. You better be prepared to handle that if you go through and throw it in there. You better have a good reason to explain why this thing could happen. But what we want to do is make sure that if those things are needed, that we have those in there. So this is why going through and screening, it starts to become even more of a pain in the ass than it was in the first semester. Because now we've got 3, 4, 5 variables to go through and account for instead of 2, right? But it's important to go through and take a look at that to try and make sure that we're meeting these linear assumptions. Questions about this? What about this one? Is this a linear relation between these two? Shaking their head, no. Does anybody disagree? Someone tell me what function fits that better than a line. Okay. It's not indicating a linear relationship, but I wouldn't say that that's nonlinear, right? It's just a scatter plot, or it's just a cloud, a point cloud, right? Is it linear? Well, kind of, in that a linear relation to, or a linear model described that just fine, in that knowing something about X tells me nothing about Y, right? But what we wouldn't call this is nonlinear because there's no other function that I can map onto that does a better job than just saying, yeah, there's nothing going on with just a linear function. So this starts to become important. I'll be going through the screen. If you see something like this where you just see, hey, it looks like a big kind of point cloud, right? It's not necessarily saying that it's nonlinear. It's just saying that these two variables appear to be nonlinear.
Is this something that we're just supposed to like buy, or is there like a formula that will say if it's like?
Generally, you go through, there are basically a lot of this can be done with plots, right? And there are different types of plots. You can request the lowest plots that will go through and kind of fit kind of a slinky sort of non-parametric or sort of non-quadratic or sort of linear parametric function to things, right? You kind of see if you get anything, but yeah, a lot of this is just kind of eyeballing it, judgment calls, and then maybe running a linear model and then the non-linear components, sort of what the incremental advantage of adding that long non-linear component is. But if you've got something that's pretty quickly non-linear, you'll be able to see it. Questions about this? All right. The linearity is pretty straightforward. We can eyeball that. Additivity, pretty straightforward too. Additivity assumption of your GLM assumes that if I'm going to have multiple predictors, that these multiple predictors contribute incrementally to my outcome. Okay, so let's say, Robert, you're looking at sort of trying to predict some sort of outcome, right? Let's try say you're looking at anxiety sensitivity or something like that, right? And you want to go through and try and describe anxiety sensitivity the best you can with some regression model, okay? Basic assumption here is that you're going to have one predictor in there that accounts for some percent of the variability in your outcome. And then what you're going to do is you're going to have another variable, and that's going to account for some more stuff. And then a third that's going to account for some more stuff. So what we end up with is something, if this is, say, total variability in your DV, right? What you're saying, your additivity assumption is you're saying, okay, my first IV gets a lot of that chunk, right? But there's still a lot I haven't accounted for. In a good efficient model, you're saying, okay, what about what's left over that's not being accounted for by that? Well, now I've got another IV2 that accounts for something a little bit different, right? And I'm going to add another one in, and it's maybe going to come over here. It's not quite as much, but it's accounting for something that's not already accounted for by other things in the model. Okay. And in a good, sort of your best case scenario, these are the types of variables that you're sort of adding in. Now, we were talking about different variables that you can add to your regression to try and to help improve the power of your study. This is the optimal thing. If this is your main thing that you're looking at, what you want to do is reduce that error term, because the stuff that you haven't explained, that goes in the denominator of all your tests, right? So if you can start accounting for stuff, variability in your outcome, and stuff that's unique, that's not already overlapped with this, what that does is it starts to increase the power of your regression model by quite a bit. Okay, that's the way to increase the power of regression outside of just increasing percent.
So is this just like moderation?
Nope, this isn't moderation. Moderation is a little bit different. This is your horse race regression. You're just trying to, and we don't do this a whole lot in psychology because like maximizing the total variability we have in our outcomes, we're a goal, right? We're generally testing some theoretical proposition or something like that. If I'm in business or econ or some other applied field where my goal is to maximize my prediction of some outcome, then this starts to become important. Oftentimes, what you say is just throwing everything in the mix and seeing what turns out, right? But what we're doing here is anything that's not being accounted for by this, all this shaded area up here, that's error, right? More error in our model, the less powerful it is. So we can start to add other predictors that start to account for stuff that might be isn't. What we're showing you to do is chip away and reduce the error in our model. Okay. Now, these are the types of models we generally run in a regression psychology. Sam, you're shaking your head, no, why?
Well, I was also wondering, like, when you're doing this kind of a model, are you like predetermining your hypothesis in the hierarchy? Or is that something that the model is like building?
It depends on how you set it up, right? You should have an idea, like we're not, psychology isn't a kitchen sink science. You're probably not gonna get far if you try and sort of pull that stuff, right? Other disciplines more so, right? But problem is in psychology, do we generally have orthogonal, so Matt, here is IV, based on this graph, is IV1 related to IV2 or related to IV3?
No, they have no overlap.
They have no overlap, they're all uncorrelated. Generally, what we end up doing in psychology is we have IV1, right? So here's PTSD and here's depression, and then here's negative affect, right? And then here's neuroticism, right? What's the problem with this model?
Everything's like interconnected.
Everything's interconnected, and what we've got is we've got highly correlated predictors. This is less useful in trying to go through and introduce stuff, because what we've got, now when we're looking at this, we only have the unique effect of IV1 and IV2. All that gets is that little piece right here. And IV3 kind of gets this piece, but all this overlap here, that just goes, that's predicted with my model, but it doesn't go to any of my regression coefficients, right? And so when we get a situations, best case scenario, we've got something like this, where each variable adds something new. Each predictor brings something new to the party, right? Here someone brought brownies, and here someone brought beer, and someone brought wine, and so there's something, everybody's bringing something new to the party, right? Here, everybody brought goddamn Doritos. We've got too many Doritos, and it's fine, but nobody gets credit for bringing Doritos because everybody brought Doritos, right? This is often what we're working with, but this is, in theory, the types of models that we should be trying to build. Questions about this additivity? Yeah.
Does it matter if all the IVs go in the same direction? So if IV2 is negative and IV3 and 1 were positive, would that?
That doesn't matter, it's arbitrary. Even with our measurement sort of scales, like I just reverse code everything, now everything's going in the opposite direction, so.
I assume.
Now, can start to have an impact if we're looking at some type of suppression effects, but we'll get into that down the road.
So just to clarify, you're doing something like additivity, like
That's what we should be trying to do, and this is where this starts to become, we have to be thoughtful in terms of thinking about what variables we start adding next. So again, Natalie, thinking about your project, trying to sort of maximize the power of this interaction that you're trying to look at. Layla's had a similar situation there with the lab-based study, so collecting 400 people wasn't an option because you had to run individually. And so the idea was, okay, we can only get this number of people. What can we do to boost the power of this test? Well, let's think about what our main effect is that we're wanting to test, and now let's see if we can come up with other things that should be related to my outcome that are unrelated to my main thing that I'm interested in. So like what other miscellaneous, what other things are existing in the satellite of constructs that might account for variability in my outcome that are completely different or orthogonal or as different as possible from or uncorrelated with the thing that I'm interested in. And then it starts to become looking through the literature and choosing carefully to try and identify stuff that would go through and count towards that. And then if you go through and add those in, you start to reduce that, you start to reduce your error, increase your R squared, and that makes your testing very individual coefficients more powerful. Understand kind of this basic additivity thing. We're going to do a lot of Venn diagrams. We're going to do a whole ton of Venn diagrams to sort of get this kind of in your head. What does our GLM look like? Looks like that. Okay, it looks like a whole bunch of nonsense. And so luckily today, We are beyond the point of trying to crank this all out by hand. You don't have to be a mathematics major to go through and figure this stuff out, okay? What it looks like for us, when we go through and run these analyses, is it looks something like this equation here, okay? So what we're gonna be interested in is the relation of depression to post-trauma symptoms in communities surviving with PTSD. We've got folks in the community who have a diagnosis of PTSD. What we're wanting to look at is the association of depression symptoms with post-trauma symptom severity. Only one predictor. This is a bivariate regression here. So what we've got for our formula, our linear model here is our expected y or our predicted y or y hat equals a plus bx. Okay? And if I go through and I actually run this model with the data, this is the formula I get. My expected value of y is equal to 2.48 plus 1x. That actually turned out to be like, okay. So this is what my general linear model looks like for this question. Okay. If I look at the data, what my data looks like. Okay. I see a nice scatter plot here. Basha, do I have a linear relation here? Yep. Is there anything that looks nonlinear? Not really, right? I mean, I can fool around trying to imagine something, but I'm just going to make my model unnecessarily complicated, right? And if I go through and I draw my regression line here, my best fitting model, what I've got here is a line that minimizes the sum of the squared distances of any one of these points from my predicted line. We'll get into this a little bit more in our regression model. Yeah.
Sorry, what is the y? That's your general linear model.
Yep. This is what my for this case this is what my general linear model looks like. It's just a basic bivariate regression model. One predictor, one output. Okay. Y hat. This means my predicted value. So if I go through and I plug things in, I'm going to get predictions that are following along this line. Are those the actual values of y? No, they're not the actual values of y, but they're my expected values of y. Right? Based on my model, this is the expected score that I would get on y, given sort of a specific value for x. Okay? Very important when we start sort of getting into this a little bit. Okay. So, thing is, show of hands, who here is afraid of equations? Okay, lots of people. That's a natural reaction. Don't be afraid of equations. Don't ignore them because they have a ton of information available to them. Okay, so if I'm looking at this, okay, we've got my general linear model here. So Matt, what's my expected PTSD score when depression is equal to 0? Depression is my X, PTSD is my Y.
So it'd be equal to A.
What's that?
Be equal to A.
Equal to A. And what is A?
24.8.
24.8, right? If, based on my model, for people who have score 0 on depression, I'm expecting their PTSD score to be 24.8, right? How do we know that? Well, if anytime we throw 0 in, and this is as we start to do this, 0 is a magical number. It's going to be very, very important for manipulating our model. If I go through and I put a 0 value in here, my expected value now is 24.8. This is my intercept, right? My intercept, that A value, is the expected value of my outcome when my predictors are set to 0. What about expected change in PTSD given a 1-unit change in depression?
25,
What's that?
25.8.
What's that now?
25.8. Like,
Yes, if I were to go from 0 to 1, but sort of keep on that logic, just in general, if I were to change my depression score by 1 unit, how much should I expect my PTSD score to change? 1, right?
okay.
So for every unit increase in depression score, I expect a 1 unit change in my PTSD score. Okay, and this is my slope. This is this number right here is determining the steepness of that line. For every unit I increase my depression score, I'm expecting that my PTSD score to increase by a significant. This is my unstandardized regression coefficient. This is qualifying in very real terms the nature of my expected relation between X and Y, okay? Now, Rachel, in all the universe, every time I see someone with a 1 unit higher score of PTSD, are they gonna have a 1 unit higher, or 1 unit higher score of depression? Are they gonna have 1 unit higher score of PTSD? No, because my model's not perfect, right? It's pretty good. It does a nice job, but I've got all this junk up here and all this junk down here, right? That's why that Y has a little hat on it. It's expected, right? Whether or not the extent to which that supports the actual reality is a situation, right? This is where we start to look at the overall fit of our model and start thinking about that. But if I'm wanting to go through a practical interpretation, I'm saying based on my model, I would expect for individuals with a depression score of 0, I expect them to have a PSYC score of 24.8. And for every unit increase in depression, I expect that score to increase by 1 point. So that equation right there, even though it might sort of look scary on the front end, starts to have a ton of information and a whole lot of interpretive value. And if I start to apply it, starts to make a lot of sense and gives much more in-depth and interesting interpretations. Questions on this? All right. So this is our unstandardized solution, but sometimes, and our unstandardized solutions, these are nice if I'm looking at things with natural units, right? Like we've talked about this before in terms of if I'm looking at, say, a bunch of body mass or something like that, something that has a tangible, like it's a real thing, it's not an arbitrary thing, right? I can say for each sort of unit increase in restriction, I'm expecting an X unit reduction in body mass, right? That could be a very powerful sort of interpretation to make. But sometimes we're using completely arbitrary measures, right? Allie, you're saying sort of a 1 unit increase on folk psychiatry measures expected to be associated with the next number of increase in negative affect or something like that. Who knows what those things are? They're not real numbers, they're completely arbitrary, right? So in some of those situations, sometimes it's nice to have, if that sort of actual units don't make a whole lot of sense, sometimes it's nice to standardize things. And this is where we get our standardized models. With our standardized model, here what we would do is we can convert all of our X scores into Z scores and all our Y scores into Z scores. And then we regress the Z scores of my Y on the Z scores of my X. And this will give me a standardized model. Does my graph change? Do the points change? In terms of the shape of the graph or anything truth there? Nope. Does my regression line change? Does that slope change at all? Nope, it's the same. All we're doing is fooling around with the units, okay? And so what happens is now in my standardized model, X and Y now have a common scale, okay? And my regression line is going to intersect at the point where both of those scores equal 0. If what does 0 mean? If X and Y are both Z scores and then my regression line intersects when X and Y are 0, what does X and Y is 0 mean?
Is that gonna be like the middle center of the,
Yeah, what do we call the middle center?
like the average?
And what do we call it for statistics? What do we call the average?
Or the center of a normal distribution.
Is a the mean.
Oh,
the
yeah,
mean,
sorry.
right? The
Average.
mean, right? So we've gone through what we find, and the same thing with the unstandardized model. What we're finding is that line goes directly through the mean, right? The mean of X, the mean of Y, that's where they meet. Our regression line will always intersect the mean of my two variables here, okay? But now what I've gone through then, because my X and my Y, the units of my X and my Y are now standard deviations, that regression slope now represents the expected standard deviation change in Y given standard deviation unit change in X. Okay? This is the impact on the model. I just have sort of simplified this down. What's the difference between this model and my unstandardized model? What do you think, Erica? What's that? I'm sorry.
Like an average in the standard.
Okay, yeah, so we're kind of looking at some averages and Z-scores. What is this missing that was in the other, in the previous equation? Yeah.
You're not adding
Yeah, I don't have an intercept in there, right? Because what's my expected value of y when x is equal to 0? 0, right? So what it does in our standardized model, we drop that intercept. The intercept is no longer there, right? Because my expected value, I already know what my expected value of y is. When x is 0, it's going to be 0. So we don't need to add 0 on anything, so we just drop that out, okay? Well, what happens if I go through and I run this, my slope changes now because my slope is now standardized. And when we use that slope is it gives us more interpretive value. You can start to interpret this kind of like an effect size, right? Now in a bivariate regression where we just have one predictor and one outcome, what is my standardized regression coefficient equal to?
Repeat that.
What's that?
Will you repeat what you said?
Yeah, if I have a bivariate regression where I have x and y, right? Just one predictor and one outcome. What is my standardized regression coefficient? What's that equal to? To be equal to correlation between x and y. You just basically drop it in. Correlation and regression, you just got sort of two variables. They're identical. Your standardized regression coefficient is going to be equal to your Pearson correlation coefficient, right? And so basically what it's telling me is for every standard deviation unit increase in x, I'm expecting the corresponding standard deviation increase in y. So here, if we take a look at this, we've got for my BDI, my x, the standard deviation is, we'll call it 12. And for my PTSD, standard deviation is 22, right? That's saying my regression model here is saying that for every standard deviation unit increase in BDI, so every 12 unit increase in BDI, I'm expecting about a half a standard deviation increase in my FAS, right? Which if I go through and look, it's going to say for every 12 units increase in BDI, I'm going to get about 11 unit increase in my CAPS score, right? And what it does is it puts both of those on a metric. And so what I can start to do is I can start to directly compare the relative strength of various predictors in my model, whereas with my unstandardized coefficients, that's harder because they're all on different scales. Okay? So I can look at that standardized regression coefficient as a proxy for the magnitude of the relation between x and y, one side of control for everything else. Now I only have one variable in here, so but this is just essentially the correlation. Questions? We'll go back through and revisit this so when we get into the regressions. Okay. So getting into the question of how do I choose my analysis grading? Anytime you're looking and trying to understand your analysis, the very first thing you should do is say, make a list of what are my predictors, what are my outcomes, or what are my x variables, what are my y variables. Look at the unit of measurement of those two things, and that information will tell you exactly what analysis that you should be running on. Okay. So for my bivariate generalized linear model, right? So I've got one predictor, one outcome. If I've got a continuous x and a continuous y, look at a Pearson correlation. I can run a regression model if I wanted to, that's functionally the same, it's just a Pearson correlation. If I've got a dichotomous x and a continuous. Okay, so my predictor is just a dichotomous variable. It's a dichotomous categorical variable. My outcome is continuous. I can run what we would call a point by serial correlation, or just run a t-test. They're the same thing. There's no difference between those. So I can run either one of them. They're going to give me equivalent. They're mathematically equivalent to one another. With the Pearson point by serial correlation, I'm going to talk about how my categorical variable is associated with my outcome. This is how the biological sex is associated or relates to some outcome. Or I can run a t-test and say men and women differ by this much, but it's functionally the same thing. I have a dichotomous x and I got a dichotomous y, two categorical variables. I'm either going to run a phi coefficient or a chi-square test. Again, they're equivalent tests. They're the same thing. If you the answer you get for one is going to be the exact answer you get for the other one. If you get differences, you've done something wrong. Okay, the functions are mathematically equivalent. So here, again, for Point by zero, the t-test and the p-coefficient and the chi-square test, they're equivalent, but they differ in terms of the, we're generally talking about the associations between this variable and my outcome versus like mean differences, group differences, or frequencies or things along those lines. So really your selection of which one of these do I want to choose is just based on how you want to talk about it. Okay, gotten into fights with co-authors who I didn't know about. I'm trying to ask them through a correlation table. I'm like, okay, well, they give me a t-test for the differences between control and experimental group on some outcome. Like, well, I don't care about that. Just because I want to everything else is a correlation. I just want to report this as a correlation. Like, no, you can't do that. So a group test says you got to report t-test. I'm like, don't. Same thing. Trust me. And so after some cajoling, finally got it in. It's like they're both equivalent metrics of the relationship. We're just talking about it a little bit different. Do I want to talk about these group differences or the association of experimental group outcome function? To see how this is these, we start to see can move back and forth between different tests that are going to be functionally the same. And next week we'll go through and start to get into some of this stuff. Benefits of conceptualizing this generalized linear model as relations. Part two is we start to add more variables in. It starts to become easier to say this is the relation between x and y. This is how x and y are associated. x1, x2, x3, those types of things. And so what we can do is we can start to look at our simple multivariate GLM and start to add in more predictors. So it's not just one predictor, it's multiple predictors. Let's say I've thrown a bunch of dichotomous predictors of some outcome. It starts to become hard to talk about differences in x and y, controlling for differences in this, controlling differences for that. It starts to get cumbersome. It starts to be easier to say, this is how this dichotomous variable is related, this categorical variable is related to my outcome controlling for these other things, right? It starts to free things up. And we can start to think about my expected value, my predicted value, my outcome as the sum of my weighted predictors. Remember that additivity thing that we talked about, right? If I go through and I say I have this information, I can predict X, and so this is. And if I add another one in, I can make an additional adjustment. And if I add another one in, I make an additional adjustment. You continually hone in on a prediction that's more and more accurate relative if I just have one variable in and of itself. So for example, let's say that I want to the association of depression, trait anxiety, and social support with PTSD scores for unmotivated function. Okay. Before we were looking at the relation between or the association of depression and PTSD. That was our bivariate model, right? We just had two variables. Here, we're adding more into the mix, right? And so if this is my standardized equation, so we're thinking about additivity, I'm saying, should Ali, based on this equation, which one of these predictors is holding the strongest association with my outcome? Depression, right? And how did you know that? What's that?
What's the largest value?
Yeah, it's the largest value. And this is the value of these standardized regression equations. And we can start to go through and take a look at relative strength, right? Now, there's some statistical procedures we can say, is this mean or sort of is this a real difference or things like that? That's rarely of tremendous level of interest, right? I can see this is very clearly a larger value. So a stronger association between depression and outcome control for everything else. And once we do that, we see some continued association of these other two, right? But the idea here is that depression is accounting for, of this set, a pretty good predictor. And then we add anxiety, trait anxiety in, and it adds a little bit more to the predictive value. And then we add in social support, and that adds a little bit more of the predictive value. Now, these things, depression, anxiety, and social support, that's probably going to look more like that graph than that graph. So it's not an entirely efficient equation, but there's often types of things that we do. And so basically we're seeing that as we add these additional predictors in, they're starting to add to the fit of my model. Yeah.
So with social support, you're having a negative value too, is that
So basically what this is saying is like, okay, I have my depression score, right? And I'm predicting my outcome based on depression. I'm giving an expected value of Y. But then I'm gonna take that and I'm gonna add 0.14 standard deviation units for every standard deviation unit increase in anxiety. And then what I'm gonna do from there is I'm gonna take that and then I'm gonna subtract 1/10 of a standard deviation for every standard deviation unit increase. So basically, I'm just going through, making an adjustment, and I add the other thing and subtract, add, subtract, try and hone in on something. It's gonna give you a greater predictive value than any one of these individually. So, yeah.
So does the order matter, or like how do you go about like?
We will run simultaneous regressions in this class. We'll talk about stepwise regressions and things along those lines. They're not typically tools that we see used a lot within the context of psychological science, because it's just a throw everything into the hopper, right? And we'll talk about some of the limitations of that stepwise regression. Here, everything goes in. It's that second graph over there. Everything that's shared, that gets, no one gets credit for it. If you brought the same thing everybody else brought, no one gets credit for that, right? That all goes up to sort of the house pool, right? Everybody gets to, so we like it, but you don't get credit for it, right? But the stuff that you bring in uniquely, that's what's being captured right there. Okay. This is different than a stepwise regression where here IV1 gets everything because it was entered first, and then the lead-ins get left up to the other folks. And they go over what the problem is. That's generally the selection of models. Empirical models are based on like bivariate correlations, say. And if I got two variables, one's correlated 0.23 and another correlated 0.24 with my outcome, which one gets to jump in first? 2.4. The difference between 2.3 and 2.4 meaningful. If we were to rerun this analysis, do those be flipped? Absolutely. If one completely fall out, sure. So we've got problems with replicability and capitalization on sample specific features.
Also, how do you know when to stop adding things? Like, last semester we talked about like not wanting to add too many
Yeah.
things, but it seems like with this, it's kind of the opposite. 'Cause you want to account for as much as you can, like.
Your reviewers will crucify you. Essentially what happens. This is a different thing in terms of if I'm looking at like right, where I've got millions or billions of observations. I want to throw 500 dummy variables or something way to look at. I care about that, right? For psychological science, our stuff is theory based, right? And so if you just start throwing things in just because people aren't like that, because one, all this stuff is going to be related to one another. You're going to have redundancies in the model. You're going to get taxed for that. You're going to start to have some problems. So you want to be careful when thinking about the variables that you're including in. Now, you can't have more variables than you have observations, right? That's rarely an issue. Back in like the 60s, right? I want to run a regression model with 20 people, and I've got 15 variables. They were more concerned about that. It's rarely an issue now. I just want to be kind of reasonable. So probably like these are regression models would handle more variables than reviewers will generally want to see in there. The risk you run is in a paper just saying like, hey, we just threw everything in there just to see what sticks, which is generally not works. Other questions? All right. So another thing to remember here in our use multivariate form, remember in a bivariate situation, if I'm just looking at the relation between X and Y, in my regression model, the standardized coefficient is equal to my Pearson correlation. It's the same thing, right? As I go through and I start to add into the simple multivariate form, now I've got multiple predictors. Those standardized coefficients are no longer equivalent to correlations. These are partial coefficients. So this represents the relation of X and Y controlling for other variables in the model. So you can interpret these as correlations in a multiple regression setting. My simple multivariate GLM, I've got a continuous X and a continuous Y. I'm talking about a regression model. I've got a discrete X and a continuous Y. So I've got a categorical X value. So oftentimes this is a nominal variable. I'm looking at different groups of populations and a continuous outcome. This is my ANOVA. My one-way ANOVA, I've got some moving variable, condition 1, 2, and 3. I'm looking at that nominal variable and its relation to some continuous outcome. We're talking about that. I've got a mixture of continuous and categorical X's and continuous outcome. Talking about an ANCOVA. This is an interesting model, kind of a marriage of regression and ANOVA. We'll talk about that as we get towards the end of the semester, but we can go through and do this. If I've got a continuous X's, categorical outcome, talking about discriminant function analysis. You don't see much anymore because we've got better tools, FA, but historically this is what we would do. If we've got a mixture of continuous and categorical variables and a categorical outcome, talking about a logistic regression is a super powerful model that's really cool, underused in our field, but we'll talk about that a little bit. If I've got a mixture of continuous and categorical X's, and I'm looking at time to something happening, this would be a survival analysis. I've got measuring time and a mixture of continuous and categorical variables and a continuous outcome, looking at time series analyses, right? So, show of hands, who here has access to the Tabachnik text?
Which one was that?
The Tabachnik text?
That's the multivariate.
The multivariate
text.
statistics, yeah.
Everyone should have it because we all had it last semester.
The book?
Not the how, not the how.
Oh,
So,
no, I don't have that.
I would encourage you to find a copy of that textbook. One, you'll need to have it anyway, because I'm going to give you an in-person quiz on it. But in terms of if you have any designs of doing research capacity, that's just a standard reference to have. It's very, very good. So at the very least, trying to score yourself an electronic copy. It's on the syllabus. Want to have that. And again, when you start to go through and look at stuff, as before, I mean, we can come to class, talk about stuff, and I'll present stuff in class, but to the extent that you can go through and read those assigned chapters ahead of time. So do look at, so the reference, the texts for this class are good to have on in your library. It will serve you beyond this class, unless I'm not doing research, which is going to be something to navigate, but make sure that you have access to a copy of this. It's an investment worth making. Okay. In that text, what you'll see in the appendices is kind of a branching graph of sort of decisions to make for analyses and things like that. Really, really nice. And again, if I know what my variables are and the level of measurement, I can go through and follow that and figure out exactly what analysis or what types of analysis I should do. Okay. Up to this point, limitations. Okay. Criticisms or bivariate analyses, we can also make arguments against my simple multivariate model, right? Limiting ourselves to simple multivariate models can be cumbersome and inefficient, right? Remember, our simple multivariate model has multiple predictors and a single outcome. Well, what if I have multiple outcomes, right? I start to become limited in the types of things I can go through and look at, right? So what if I have multiple related outcome variables, right? So what if I'm interested in the relation between gender and college performance, right? Well, how do I measure college performance? College performance is a whole lot of stuff, right? It could be course load, class attendance, hours studied, GPA, major GPA, subjective investment in university life. These are all things that are probably going to have some association with one another. Now, I could go through and just look at, have a model for each one of these outcomes individually. Then I'm going to have a whole lot of models, right? Maybe if, I don't know if you've done this, but if you're doing it on man, what types of sort of, what clusters of outcome variables might you put into like a manual model?
Is that like when you, like categorize, what do you like?
Not really. So if I was looking at sort of, let's say, different things that you might look to be associated with substance use, like sort of days drinking, sort of motivation, sort of those types of things, right? I've got maybe 3 or 4 different outcomes that I'm interested in, and those outcomes are all going to kind of correlated with one another. I could go through and run a single or a simple multivariate model with looking at each one of those outcomes individually. Or what I could do is I could run a full general linear model that's looking at a set of predictors in the relation with a set of outcomes. This is going to take us to our full multivariate form here. Our full multivariate form, we got multiple predictors and multiple outcomes. Okay, I've got my y1, y2, y3, so on and so forth is equal to z1, z2. So I've got a bunch of outcomes regressed onto a bunch of predictors. Right, this is starting to get pretty big, complicated model. There are additional complications, but these are things that we can go through and run. Okay. Now, mathematically and conceptually, the leap from going from a simple multivariate where I've got a bunch of predictors, I'm trying to predict one single outcome. My full multivariate, where I've got multiple predictors looking to predict multiple outcomes, is that I often will need more than one equation in order to account for that. What we're sort of transitioning to is looking at a series of equations to mathematically represent sort of my model. Okay. Kind of analogous to sort of basic algebraic, right? Natalie, x plus y equals 24. If I tell you that, tell me what x is equal to. All I tell you is just x, hey, guess what, Natalie? X plus y equals 24. Tell me what x is. What's that?
I don't know.
I'm sorry, what's that?
I don't know.
You don't know. Can you say a number? Any number. 2. Yes, you're exactly right. Say another number.
8.
Maybe. Say another number.
13.
For sure. Why not? Right? We can throw in any number of sort of, if all I'm doing through now, once I say a value for x, then y becomes fixed, and then so that's something different, right? But if all I have is x plus y equals 24, I don't have a unique solution to that, right? There's an infinite number of solutions to that equation, right? But if I go through and I add in a second equation, right? Now I'm saying x plus y equals 24, also 2x minus y equals -6. Now all of a sudden I've got 2 sets of equations, and now that's solvable. I can come up with a unique solution for that, right? Because presumably my chosen values for x and y have to be true for both of these, right? So with just one, that's the situation we're running in. If we have multiple x's and multiple y's, one equation is generally not going to do it because I can't come up with a unique solution. So we need to have multiple linear equations sort of built in order to find a unique solution for these models. And if I don't have a unique solution, then the problem is, back why we care about unique solutions, well, because otherwise it's a free for all. You say, I don't know, so make up a number, whatever you want it to be, because it all works out. Okay. So we're talking about these full multivariate GLMs, right? What we talk about in terms of these equations or these linear combinations of variables changes depending on what type of analysis we're talking about. Sometimes through these characteristic roots, that's like a DFA term, or principal components, that's a factor analysis term, and it kind of varies, but it's all basically the same thing. Okay. And in general, for these analyses, what we find is there exists as many roots as the smallest number of x or y variables in the model. So if I've got 5 predictors predicting 3 outcome variables, I would have 3 characteristic roots or 3 equations that could fully capture this, right? If I've got 5 outcome variables and 2 predictors, then it's going to be 2. Okay. But the thing with this is, as we start to look at this, the number of roots that we need to account for a set of variables is often less than the full number of equations possible. Okay, so for now, we've done run some stuff with factor analysis, right? To fully account for, let's say you've got 12 indicators, right? How many factors or how many components can you extract from a data set with 12 indicators? Yeah. 12, right? Is a 12-factor structure with 12 items, is that a useful solution? No, not really, right? So there's generally a lower number that we can go through and extract from that to go through and try and sort of separate or identify this stuff. This is kind of hard to wrap your head around, and don't worry about this too much because we're not going to get into fully multivariate designs. We're going to sort of get you strong on basic general linear stuff, and then sort of if you want to go on and explore sort of fully multivariate models, you can sort of go through that. But just try and wrap your head around this. Let's say we're looking at the association between P predictors, so a set of predictors, right, and a pair of outcome variables. So I've got a bunch of predictors and just two outcome variables, right? We're looking at self-esteem and extroversion here. Okay. And let's say the geometry of this puts self-esteem and extroversion right there, right? What I've got here is I could use one equation to go through and separate these points. Okay, so my one equation, the sum of beta P1 Z X P1 here, that's basically saying a bunch of those all added together, basically. So my regression model. So this is one thing. And if I go through and with this equation, I can go through and separate self-esteem and extroversion from one another. So based on this equation, I can differentiate self-esteem and extroversion. And so I'm feeling pretty good about this. What if I add a third outcome? What if I say, okay, I want to add social desirability to the mix? So now I've got a set of predictors. Now I've got three outcomes. Okay. And if I go through and I plot this in 5-dimensional space, this is where social desirability falls. Okay. If I'm looking at this, is my first root capable of differentiating on my outcomes? Elizabeth, you're saying no. Why? Explain why not.
Because the social desirability and the extroversion, because they're like on say the same line, it's going to be hard to distinguish. Like if you're looking at self-esteem, how are you going to know if it's related to the social desirability, if it's related to the extroversion?
Absolutely right. Right. I can't tell with this equation. Social desirability and extroversion line up at the same time. I can't differentiate those two. I can differentiate self-esteem and extroversion, and I can differentiate self-esteem and social desirability, but I can't differentiate social desirability and extroversion because I'm sort of one-dimensional plane there. They exist in the same spot, right? So what I can do is then I can go through it and extract another root, right? Another equation. And now with this set of equations, root 1 and root 2, I can differentiate all three of these points, right? Because I've got, now does root 2 differentiate self-esteem and extroversion? No. On root 2, self-esteem and extroversion are indistinguishable, right? But I can differentiate social desirability and extroversion, social desirability and self-esteem. So in this situation, we can think about this in 8-dimensional hyperspace, right? Like, so what we do, these two equations, these two roots together give me a full accounting for my outcome variables that I have. Kind of seeing this visually, very simplified kind of way. And so what if I change, what if social desirability doesn't exist there, or social desirability exists right there? Do I need that second root? No, second root doesn't actually do anything. My first root is not good, right? So even though I have three variables, just that one root does a fine job of differentiating those. So just because I have extra predictors in there, I don't need those to go through and differentiate, right? So it just it requires sort of me some advanced interpretation to go through and determine like how complex of a model do I need to achieve the thing that I'm trying to do, which is differentiate of outcomes. So this is, don't worry about this too much. This is just kind of a brief introduction to the types of issues that we get into fully multivariate designs. Now, the problem is that fully multivariate designs seem kind of cool because we can go through and have multiple predictors with multiple outcomes. But just like, remember when we had, like, cool, now I can have 3 groups, 4 groups, and see if I've got differences across those. Design, if I did find differences, was that the end of my task? What did I have to do afterwards? Figure out where they were. Same thing with multivariate designs, right? Particularly with the fully multivariate design, things like nano. So let's say I've got multiple predictors looking at multiple outcomes. If I find this overall effect of my this effect of that nano that says that, yeah, so these groups are different on the best linear combination of this set of outcomes. Now I find that now I probably have to go back through the individual ANOVA models and then now we test it individually. So once again, there's no free lunch, right? So fully multivariate designs, at least in sort of how they've been traditionally conducted, won't see them that much anymore, right? Now, if you're looking at like SQM and things like that, then that's a different type of thing. That's a different system of linear models. That's generally kind of the form it takes. There are a lot of advantages to that. But historically, if I've got a lot of continuous X's and a lot of continuous Y's, we've got some canonical correlation with that. If I've got multiple discrete categorical X's and a number of continuous outcomes, that's where our manual is coming in. A mixture of categorical and continuous X values and continuous Y values and COVA. We've got discrete categorical X predictors and continuous observations. This is where we get into our repeat measures ANOVA. This is one that we will spend some time with. If I've got latent predictors, right, and unobserved predictors and continuous outcomes, this is where I get into principal components and principal factors, right? And now it's stuff out in one of these factor analysis. If I've got a bunch of observed outcomes, and my hypothesis is that there's some underlying dimensions, some unobserved dimensions that's giving rise to variability and clustering that we see in these observed scores. This is when we're sort of looking at some principal components, principal factors. And then if I've got a whole big old group of interchangeable X and Y's, continuous categorical, and sometimes X's are X's and sometimes they're Y's, depending on how I put it all together. Now we get into SCM models, right? And these are really, really nice, flexible types of models. And so if you have a strong foundation of regression, SCM is pretty. But this would be examples of fully multivariate. But again, going back, and this just hitting this on the head, not to pick on Brittany, but this is a big question a lot of people have. Hey, I've got this study, but I have no idea what I'm going to run this terms of analysis. Seems like a daunting task. It's actually not. Make a list of your X's, make a list of your Y's, determine level of measurement for each one of those, and that is going to narrow down your options quite a bit. So, all right, that's it. Welcome back, everybody. We made it through. We're doing good on time with this. So, what we'll do next week. Now, some of you will be here, some of you won't. There's going to be a lot of ins and outs in terms of responsibilities for interviews and things along those lines. I'm fine with however you want to do it. Like, I understand that you have lab obligations and things like that. So sneak in, sneak out, sort of however you need to. We'll go through and have this recorded. It'll be posted. Again, next week, we're going to get into some basic correlation stuff, and then hopefully start to get into some of the repeated measures ANOVA. You'll see in that in those lecture slides, there's a whole section on matrix algebra. I had to do matrix algebra in my multivariate class. I'm not going to make you do matrix algebra because I've got other things that, I mean, if I had the time to make you do matrix algebra, I would for sure make you matrix algebra. But I got other things that I sort of want to get to. And so that's just more for your reference. But so don't worry about trying to get sort of tied up in that. But do make sure that you get access to a copy of that attachment help text. Also, make sure that you do get access to a copy of that Aiken and West text. That's a frustrating, like tiny little skinny paperback that's more expensive than you think it should be. Is that a hardback, Aiken and West?
It's the one from the library.
Oh, you stole it from the library. Okay. Slick. All right. Well, statistics texts are always expensive, but the stuff that we've got, it's been out for a long time, so you should be able to pick up used text on the cheap. Who you use? Are you aware of the website ADDALL, ADDALL.com? Okay. Look there. Basically, it just comes out, it's so sweeps eBay, Amazon, so the third-party sellers and stuff like that for used textbooks. Make sure you buy some stuff from someone who has got more than like 3 ratings. I got ripped off once on, like, oh, that's cheap. Took all my money. Nothing ever happened. I didn't do anything about it like a punk. But go through and take a look at that. Trust me, these are going to be important resources to have. So awesome. Thank you, everybody, so much. Excited for the semester. Yeah, let me know if anything comes up.